Well, hello, calculus students and seekers of truth. In this video, we will do the trickier part of the work we did before with derivatives, which is trying to make sense of what this all means. Okay? And to help us understand that, what I've done here is I've graphed the equation, and then I've drawn this line right here. This is called the radial line, just so that we can see that this is how much we rotated. Okay, and at when theta is equal to pi over 6, we're at this point right here. Okay. And so you can kind of imagine it this way, that you can think of it as a particle. Now we'll get to the particle in the next lesson, but you can imagine there's an object that's kind of moving along this red path. Okay. And as it moves along, it traces out this like apple shape thing. Okay. And at this particular moment, when the object has reached this point, there's a bunch of things that are changing. The distance that between this point and the origin is changing. The distance between this point and the y-axis is changing. The distance between this point and the x-axis is changing. And then the tangent lines are also the tangent of this curve is also changing. Okay? And so let's just make sense of all of that right now. All right, so first, dr d theta is equal to negative root 3 over root 3, excuse me. So dr is the change of the radius, so that's the length of this green line right here. So that means at this particular moment, this green line segment right here is shrinking by this much, okay, negative 1.7 or so. Okay? So when theta equals pi over 6, the radius, okay, or the distance between the point on the curve and the origin is decreasing by negative root 3. And if we had units for this would be a length, right? So this would be, and it's kind of a weird unit. It's like negative root 3, let's just call it feet, per radian. Okay, so for every rotation, every slight change in the rotation, this length is shrinking by negative root 3. Now let's look at dx d theta. So dx d theta, keep in mind dx is the horizontal distance. So it's really this distance right here. I'm going to draw right here, this horizontal distance right here. Maybe change the color. So dx dt, the change in x, right? So this is what, and we're going to start, this prompts all the same. When theta is equal to pi over 6, the distance between the point and the y-axis, this x length here, so the distance between the point, whatever this coordinate is, and the y-axis is decreasing at a rate of 2. Okay. Now I realize I made a mistake in the last one. When I say decreasing and I say negative, decreasing by a negative, that's increasing. Okay, so decreasing, we should be decreasing by a positive amount. So a negative change is a decrease by a positive amount. That's a little confusing, but I'm sure you'll figure it out. So as this curve is rotating here, at this point, the distance x, the distance between this point and the y-axis, that's shrinking. Okay? And so dy d theta, y is this length right here. So the distance between the point and the x-axis is increasing. So the distance between the point on the curve and the x-axis, it increases at a rate of root 3 over 2. And again, we don't have any units here, but it would be something like feet per radian, right? Because it's relative to, it's changing relative to the angle of rotation. Okay. All right, so Now let's look at the last example, dy dx. So dy dx is probably the most familiar expression in calculus that you know of at this time. But in this context, it can get lost in the details here. Now, but we go back to basic principle. Change in y over change in x is the Cartesian slope, right? So it's, I need to draw this way better here, but let me try that again. All right, there we go. That looks a little bit better. So I used a ruler here. You should do the same. This blue line right here, right? So dy dx, that's the line that's tangent to the curve at that point. Okay? So the line tangent to the polar curve has slope negative root 3 over 2 when theta equals pi over 6. So right at this point right here. So we got a couple things, four things that we're talking about. The change of the distance between the point and the origin, the change of the distance between the point and the y-axis, which is actually dx d theta, the change of the distance between the point and the x-axis, which is actually dy d theta, and dy dx is still the slope of the line that is tangent to the curve, okay, at this particular point. All right, so I hope that helps to clarify and helps to enhance your understanding of polar functions, especially when we're calculating derivatives. This is a long lesson, a long topic, and there's a little bit more to go. So take your time with it, go slow, make sure you understand every little thing, or all of the details and nuances here, because that's the most important part. All of the messiness, you'll work that out, and I'm sure you'll do really well at it. Thank you for watching, and have a wonderful day.